Okay, everybody, you remember last time we did just simple circuits and series circuits, and if you remember, in this case, a light bulb, the wire had to touch both the side of the bulb and the bottom of the bulb in order for it to work because you need a circuit for the electricity to flow through. You can't touch both wires to the side or both wires to the bottom, it won't light up. And remember, that's because the light bulb has a little circuit inside of itself. And you need to connect one wire from one end of the battery to the side and from one end of the battery to the bottom so that electrons can flow in a circuit. Okay, and that's the key for all of this electricity stuff, that the electrons have to be able to get from the negative end of the battery through the resistor all the way to the positive end of the battery. Okay? And most batteries are 1.5 volts, A, AA, AAA, D, and C cells. They're all 1.5 volts. And then we talked about series circuits, and in this case, it's still the same. No matter, here I have the batteries. I have 4 of them in series and 3 light bulbs in series. And again, series means that the electricity has to pass through every resistor. It has no choice. It doesn't have any other pathways. So the electrons will go through every light bulb to get from one end of the battery to the other. Remember, I said that each battery was 1.5 volts. Well, in this case, there's 4 of them in series. That makes a total of 6 volts, 1.5 times 4. Okay? And the same works for whatever the resistor is. And here, let's say I have 3 1-ohm resistor light bulbs. Well, that means there's a total of 3 ohms of resistance in this system. So the batteries have 6 volts of pressure pushing the current through 3 ohms of resistance. And we can use Ohm's law, that the current is the voltage divided by the resistance, 6 divided by 3, to get that 2 amps. So this is 6 volts of pressure pushing 2 amps of electricity through 3 ohms of resistance. And this is a series circuit. Now we're going to talk about simple parallel circuits. Here the batteries are still in series, but the 3 light bulbs in this case are in parallel. And parallel means that the electrons have a choice. They're not all required to go through the same resistor. Like with a series, all of the electrons have to go through every resistor. With a parallel, there's a choice. Okay? There's different pathways, but it's still a loop. The electrons still have to go from one end of the battery to the other through the resistors, but you'll notice that they have a different pathway. Like the pink one is going through the bottom light bulb and then joins up with the others. The blue one goes through the top resistor and then joins back up with the others to get to the other end of the battery. And the yellow one goes straight through the middle, but they all still flow through a circuit from the one end of the battery through the resistors to the others. But here, like in the series one, the current was the same in all resistors, so the amount of electricity was the same because they all had to go through the same path. But for a parallel, the current is not the same in every resistor. It's the voltage that's the same in every resistor. So let's talk about circuits. And we did a series circuit. And a series circuit was where you have some sort of voltage, some sort of source, and it pushes the electricity through a series of resistors. So the electrons have to have a path through to the other end of the battery. In a series, those electrons have to flow through every single resistor, and that is called a series circuit. The electrons have no choice but to go through everything in series. Today we're going to switch to the other type of circuit, which is a parallel circuit. It's basically the same thing. You still have a source with a certain voltage, and this time the electrons have a choice of where they can travel through. I'll give you an example here. Like here, we can get to a junction point here where the electrons come up and they have a choice. They don't all have to travel through the same resistor. They still have to be a full loop. The electrons still have to be able to travel from one end of the battery to the other. But here they have a choice. They can either go down through this bottom resistor onto the end. They can go right through the middle resistor onto the end. Or they can go through any one of the resistors to get to the end of the battery. And this is called a parallel circuit. These resistors are in parallel with one another. So I want to talk to you about how to analyze one of these. Okay, so just like we did the series, we're going to break it down. So I'm going to have a parallel circuit where the electrons have a choice where to go. And what I'm going to do is I'm going to break this up. Let me give you, we'll say that this is a 9-volt battery and we have a 2 ohm resistor. We'll give it another 2 ohm resistor. And we'll say this one is a 3 ohm resistor. And what we're going to do is we're going to find out the total current in the system. We already know the total voltage. Voltage total is 9 volts. And we're going to find the equivalent resistance in this circuit. So what we're going to do is we're going to analyze this circuit to figure out what the total resistance is and what the total current is. Okay? And how we do that is we like to break this up into a string. So we like to break that battery and that circuit in half and draw it as though everything were in a line to the end of the battery. So we're talking about the electrons coming from one end of the battery, flowing through, getting to the other. Here, I like to put junctions anywhere there's a choice for the electrons. I'll label them junction 1 and 2. And what we're going to do is we're going to bring these together as though it was one resistor. So and see, these three are all in parallel. We can use, remember when they were in series, we just added up the resistance to find the total. But for parallel circuits, we have to use the reciprocal equation, that the reciprocal of the total resistance is equal to the sum of the reciprocals of the circuit. Okay, so here, and I know that this is 2, 2, and 3. So I'm going to redraw this as though it were one circuit. 9 volts, and this is going to be resistor 1, 2, 3. And I'm simply going to plug in 2, 2, and 3. Okay, so 2 reciprocal plus 2 reciprocal plus 3 reciprocal. That equals 1.33 ohms, but that's not the total resistance. The reciprocal of this is the total resistance. So then I would take the reciprocal of that and get 0.75 ohms. So this is a 0.75 ohm resistor. So this battery, it has 3 resistors. It's pushing the electrons through. But it feels a total combined resistance of 0.75 ohms. Now, that allows me, since I know the voltage is 9, and I know the total resistance is 0.75, I can use Ohm's law. Current is voltage over resistance. So 9 volts over 0.75 ohms, and I can get the total current in this system to be 12 amps. So I know that my total resistance is 0.75, and I know my total current is 12 amps. Now, I can work back up and find the total voltage and current at each and every individual. So I compressed this circuit down to one equivalent resistor, found the total amperage, and now I'm going to work back up. If you remember, for series circuits, the current was the same everywhere because the current had no choice. It had to go through every resistor. But for a parallel circuit, the voltage is the same everywhere. So I know that in my equivalent resistor or circuit, I know the total voltage is 9. And in a parallel, these were a parallel circuit. That means each and every one of them is 9 volts. Okay? And now I know that this is 2 ohms at 9 volts, 2 ohms at 9 volts, and 3 ohms at 9 volts. And I can use Ohm's law, which is I equal V over R, and I can rearrange it for I just solved for current, sorry. I is V over R. Okay, so it's V 9 over 2, or 4.5 amps. And since this is also 9 over 2, so this is 4.5 amps. This one is also 4.5 amps. And this resistor down here is 9 over 3, or 3 amps. So I can analyze this circuit by combining it all into one equivalent resistance, finding the total current, and then for series circuits, taking the current back up to what it originally was. And for parallel, I can take the voltage up to what it really was, and then I can, at each resistor, solve for the current. Now this, the key to this is worked out, and it's on Canvas, and your homework today is to solve one of these simple parallel circuits for total equivalent resistance, total current, and then work back up through and find the current and voltage at each and every one of the resistors.